Saya baru realise that bila saya cakap bahasa Melayu memang video saya akan jadi lagi panjang. Sebab tu sebelum ni saya try to speak in English so that it will shorter the time. Kalau tak bergejam-gejam jadinya. In this topic we continue. When we have multi-component gas system, this is a process and application in chemical industry. The first one is absorption process. This one, absorption process, or we call it a scrubbing. And then the second one is stripping process. These two processes involve liquid and gas. So in absorption process, it is when we have gas A and B. There are two components. Enter this absorption tower, it will contact with gas C, and then it will contact with liquid C, and then from this liquid B, daripada stream ni, it will transfer into this liquid. Some of the B will be transferred ideally, and we want if it is perfect. Perfectly memang dia akan transfer, semua B akan dilute ke dalam liquid C. And then the only left gas A yang akan keluar. So jangan pening-pening. It just when a mixture of gas is contact with a liquid, so gas B will diffuse in this liquid and come out here. So only gas A is come out here. And it is opposite to the stripping process, whereby the liquid, the liquid C, which is this one, this liquid C and gas B masuk dalam stripping tower. We have another gas, which is gas D. So this time gas D ni yang akan ambil gas B. Dia yang ambil. Keluarkan tinggal liquid C sahaja. This stripper and absorption process and stripping process is always came together. And when we connected these two process together, the diagram will look like this. So again, when we have a feed gas of A here, go into the absorber, a liquid, will take, the gas B will dilute in liquid. So left only product gas, which is gas A only. So this liquid A, liquid and gas B will go through a heater to heat up the temperature, and then goes into this stripper. And then another clean gas, will take the gas B, come out with it. So why I'm telling you this, because I will give you an assignment to calculate, to do a mass balance about this stripper and absorber system. In this next example is also about absorption, whereby when you have a gas stream, we have a gas stream at 100 pound mole, it is a mixture of SO2 and air. We have SO2 and air goes into the absorber in contact with a liquid. This is the liquid, which is a liquid water, and it occurs at temperature 30 degrees C. The liquid leaving the absorber is analyzed and found to contain 2 gram over SO2, 2 gram of SO2 per 100 gram of H2O, which is this one. And then assume that gas and liquid stream, this one, leaving the absorber are at equilibrium. at 30 degrees C is 2. Okay, this is the gas stream. Okay, this is only a gas. Okay, this is the liquid. Okay, and this is not 100%. Okay, previously here it is 100%. All the gas A, okay, all the gas B will dilute into this liquid, and there is no gas B here, right? But in reality, it always have the remaining of SO2 here. Okay, in reality, it's still there. Cannot be 100% separate. Okay, what we do is we need to calculate. Okay, we need to calculate the fraction of SO2 enter the water, which is at this stream. How much actually the water is absorbed. Sorry, how much the SO2 is absorbed in water, and then how much the required water feed rate, which is this value. How much we have to determine. Okay, so this example is a real example on how to do a mass balance on this when we have a condition of liquid and gas at the same time, and how we do a mass transfer. Okay, let's proceed. Okay, the first thing is 1 atm is equal to 76 mmHg. Okay, and then the next thing to do is you have to get the partial pressure of water and SO2 at this temperature, at 30 degrees C temperature, which is from Paris Chemical Engineering Handbook. Don't worry, if I'm giving you the equation, like this, I will provide this data. Okay, and then you don't have to go and open this Paris Chemical Handbook. I will provide you enough data. Okay, that this is the value of vapor pressure. Partial pressure. So from partial pressure, you can determine the value of Y. Okay, which is 300, which is 310 over total pressure is this one. Okay, and then for the SO2, same. So you can directly determine what is the value of mole fraction here and here, together with the mole fraction of air. Okay, and then we can do a degree of freedom analysis, which is we have 3 component balance, and then we have 3 info from partial pressure, which is we can determine a mole fraction from a partial pressure. Okay, the value of P, small p, is called partial pressure. Okay, the value of P star is the vapor pressure. Okay, and the value of big P is the total pressure. Okay, so P is a total pressure. Okay, and then we continue. Okay, so we can do a balance of air, which is how much the air goes into the system and the air out from the system. Okay, so we already know what is the mass fraction, the mole fraction of air, so we can determine the value of Ng2. Okay, and then the mass fraction at this stream. Okay, the information given is the ratio of SO2 over 100 H2O. From there, we can determine the value of mole fraction, or the value of mass fraction in a liquid phase we use Y. Okay, this is another thing that you have to remember. Y is a mole fraction in a gas. Okay, mole fraction in the gas, and X is the mass fraction, but in liquid. Okay, don't get confused. Okay, so because this stream is a liquid stream, okay, it is a liquid, so we use X. So for gas, we use Y. Okay, and then we can determine what is the mass fraction of X, which is this one. Okay, we have the mass fraction of SO2. Okay, mass fraction of SO2. So we can determine the mass fraction of water, 1 minus the mass fraction of SO2. Okay, this is mass fraction, okay, not mole fraction. And then the next thing to do is we have to do a balance. Okay, how much the SO2 goes into the system, which is this one to this one, okay, in equal to out here at this stream, okay, and also out here another SO2. Okay, so we already know what is the mole fraction of SO2 in gas, what is the mole flow rate of gas, what is the mass fraction of SO2. Okay, remember when you have a mass fraction here, you have to divide with a molecular weight. Okay, you have to divide with molecular weight so that you can get the mole fraction. Okay, that's why we divide with this molecular weight so that everything is in mole. And then we can determine the value of L2 here. Okay, and then we have to do a H2O balance, a water balance, because we really need to determine. The question asks for the value of L1. Okay, so we do a balance. How much in will be equal to how much the water is out. Okay, the water out and the two out here and here. Okay, so meaning to say some of the water will evaporate, goes into this system, goes into this gas stream, and some of the SO2 will dilute into this SO2 stream. SO2 will dilute into this liquid stream. Okay, and then we can calculate the value of water fed into a system. Okay, the value of N2 we already get previously. The mole fraction of water in vapor in gas state is this one, and then the value of mass fraction of water in liquid, which is the X, together with a total mole flow rate of that stream, so we can get this value. Okay, the next thing is we have to calculate how much the fraction of SO2 is absorbed, which is how much is a ratio. Okay, and how much is absorbed, it is here, is how much it came out here. How much it came out here we can calculate from a mole fraction, from a mass fraction. Okay, from a mass fraction to, and then we divide it by how much the SO2 is fed into the system. Okay, don't forget, don't confuse. This is a mole, this is a mass, and then we have to time with a molecular weight of the SO2. Okay, you have to really take care about the mole, the mass, and how you can convert it into each other. Then you get this ratio. Okay, if you have any question, you can contact me later, because it's really hard for me to have I try my best not to have a long explanation. I'm afraid that this video will be really long. Okay, so the next thing is about, there are two laws. Okay, it is Raoult's law and Henry law. This law is to relate the partial pressure, okay, to relate a partial pressure into the mole fraction in liquid phase, which is the X. Okay, that is this law. Okay, and then really depend on the value of X. For the Raoult's law, the value of X, which is approach 1, close to 1, which is when you have the value of X maybe more than it approach 1, near to 1. And then for the Henry law is when you have the value of X really small, 0.0 something, 0.1, really small value of X. Okay. And then the value of HA is a Henry law constant, which you can find in a Paris Chemical Handbook. Again, don't worry, if I'm giving you the equation, I will give you the constant together. And then this is condition whereby you have a gas liquid, vapor liquid equilibrium. Okay, the vapor and the liquid is in equilibrium, and it will obey these two laws. Okay, how are we going to use this law? We're going to see in the next example. Okay, so in this example, you have a gas containing 1 mole, okay, 1 mole of ethane, 1 mole percent of ethane in contact with water at this temperature and pressure. You have to estimate the mole fraction of dissolved ethane, meaning to say the value of X. Okay. X is always for mass or mole fraction in liquid. Y is always a mass fraction or mole fraction for gas phase or vapor phase. Okay. And then because of the value of mole, it's quite small, which is 0. If we put it like this, it will be 0.01, which is close to 0. Okay, approaching 0, so we use Henry law. And then this is the constant. Okay, this is the constant of Henry's constant for ethane. Okay, and then we want to determine the value of X A, which is X for ethane. We have a pressure 20 atm. We have the constant, and we also have the value of Y. Okay, the value of Y, which is 0.01. Okay, and then we can straight away get the value of X. Okay, so this constant, this Raoult's law and Henry's law is a relationship. How do you relate X and Y? Okay, to relate between X and Y. Okay, So X is a mole fraction, Y is a, okay, X is mole fraction in a liquid. Sorry, it's typo here, in a liquid, and this is a mole fraction in a gas. Okay, so for the second equation, it is equal molar liquid mixture of benzene and toluene, okay, is in vapor at 30 degrees C. What is the system pressure, which is P? What is the composition of vapor, which is Y? Okay. So this is the example, and we will use a Antoine equation here to determine a vapor pressure. Okay, a vapor pressure of benzene, okay, at 30 degrees C. Okay, this vapor pressure of benzene we can determine from this table. Okay, so choose benzene here, take the value of A, B, and C, substitute into this equation. Okay, and then you can get the vapor pressure of benzene at 30 degrees C. Okay, vapor pressure at 30 degrees C. And then the vapor pressure of toluene. Okay, the same method. The vapor pressure of toluene. Okay, you have to be careful with the unit because here is a degree C. Okay, no need to convert it into Kelvin. It is in 2 degrees C. And then 30, same goes for the toluene. Okay, and also be careful with the unit of pressure in mmHg. Okay, so the next is how do we calculate? We want to determine the value of Y, right? So we use this equation. Okay, we have the equal molar, meaning to say the mole fraction of a liquid, of these two liquid, is the same, which is 0.5 and 0.5. That is the meaning of equal molar. Okay, the value of X is the same. So the value of X times the vapor pressure, okay, you will get this one and this one. So we just total out this, we get the total pressure or system pressure. Okay, total pressure or system pressure. And then from this equation, we can determine the value of Y, and the value of Y for benzene and the value of Y for toluene. Okay. The next thing is when we have a solution, when we have a multiple component, when we have a multiple component in a solution, that is this Raoult's law, okay, will consider each of the species. Okay, each of the species, whether you have 3 or 2 or 1, not 1, it should be more than 1. If you have 3 species, you have to consider each of the partial pressure of that species, for A, for B, C, D, and whatnot. Okay, and then the mole fraction is also have to be considered based on the specific species. Okay, and this is also the in a liquid phase, the mole fraction. Okay, this time is the total partial pressure, and this thing is the mole fraction in liquid. Again, you have to consider each of the species. Okay, regardless how many species you have, okay, you have to consider each of the species. Okay, and The next thing to introduce to you the term, which is dew point temperature, bubble point temperature. Okay, so a dew point temperature basically when the temperature in which the first liquid droplet form when the gas is cooled down. Okay, when we have gas and liquid and we reduce the temperature until at one point the first liquid droplet will start to drop, will start to form. Okay, at that temperature we name it as a dew point temperature. Whereas a bubble point temperature is a point whereby when we heat up, okay, we heat up this liquid, okay, the temperature is increased at any point when the first bubble start to form, that temperature is called a bubble point temperature. And this is occur at constant pressure. Okay, so this is just to tell you the definition of dew point temperature and bubble point temperature. Okay, the next is okay, this is when we have the condensation and also when we have evaporation. Okay, the next thing is the dew point pressure and bubble point pressure. Okay, a dew point pressure, it is opposite from it is when you heat up, when you compress. Okay, when you compress, meaning to say you increase the pressure. Okay, when you increase the pressure, when this gas, okay, will form a liquid at the first liquid droplet form, that is called the dew point pressure. Okay, so dew is when it become a liquid and bubble when it start to form a gas. Okay, and when you reduce the pressure, okay, when you reduce the pressure, and then the liquid water will escape to form a bubble, that time is called a bubble point pressure. Okay, and this occur at constant temperature. Okay, and then a multi-component gas system will be also can also be represent by graphical method, which is these two method, these two graph. Okay, for the benzene and toluene. Okay, this is a vapor liquid equilibrium curve when you have benzene and toluene and it is at equilibrium. So this is the diagram. Okay, this topic you will see again in another subject called thermodynamic, but here you've been introduced to a few terms for you to get familiar, so that later on when you learn in your thermodynamic, you are not so confused. And I am really sorry that it has been very long delay for me to do this video, and this video also not really perfect because I'm quite rushing. It's very challenging for me to complete the video while I'm at home. Okay? And I really hope that you can still follow. At least you get some idea what is about this multi-component all about. And there are terms that you have to get yourself familiar, which is when you have P star. Okay, this P star is a vapor pressure, and this vapor pressure is changed when the temperature is changed. It's really depend on the temperature. Okay, really depend on the temperature. You have capital P, which is a system pressure. okay, a system pressure, or we call it as a total pressure. We have small p, okay, it is a partial pressure, okay, and there are a condition whereby this partial pressure equal to this vapor pressure, okay, and then this value of vapor pressure you can refer to the table, okay, refer to the table B3, and then the term you need to know, which is dew point temperature and pressure, and also bubble point pressure and temperature. What else? You need to know about the vapor, okay, the vapor, it have a saturated vapor, and it has also a superheated vapor, okay. And then for the saturated vapor, is easy to condense, okay, easy to condense. And then for the superheated vapor, we still can make it condense by using a compressor or condenser, which is we reduce the temperature or we increase the pressure in order to make a superheated vapor condense. Why we want to make a condensation? It due to we might want to separate, okay, we want to separate the gas, the species from a mixture of gas. And you also been introduced to what is a absorption process. Later on you will learn in detail in another subject, okay. All in this topic you will learn again in another subject in the future, but I really hope that you get some idea about it. And then you also have the value of x, the value of y, okay. The y is the mole fraction or mass fraction in a gas phase, and the x is the mole fraction or mass fraction in a liquid phase, okay. And then the rest is the example, not as much as previously, because this topic is really complicated, and for me also have really study to make sure that I can give you a correct idea about it, about all about it, okay. And then I'm sorry for everything, and later on please try to answer the tutorial question, and also there will be another 2 assignment from me that I will post as soon as possible once these recorded lectures is uploaded. Okay, with that, thank you very much for your time. If you have any problem, just contact me. And I'm really sorry if I cannot make you really understand this topic. I don't blame you because it's really complicated topic, but just try your best to understand, okay? You have to open your heart to understand the knowledge, okay? With that, see you later, maybe in a lab session. Thank you.